Alright guys, so here we've got a 2016 BMW. It's a 528 and it was towed in. The customer believes he has Valvetronic issues. It does have the classic rattle noise when you open the door or close it or power up from the Valvetronic motor. Naturally, I end up just doing a complete system scan to see what fault codes we got. Now, Valvetronic issues here on the channel are nothing new, but one thing that I wanted to kind of show or display, this is the scan data. Again, it's a 16, 528, 95,000 miles. One thing that is a concern to me, not really see all the time. Again, this vehicle is coming towed. I don't know anything about the condition of the engine, transmission, everything overall, since it just cranks in those starts. We have a trouble code related to engine being too low. We've got this knock sensor signal, noise above limit value. Those two right there are concerning to me. And then here's another one, sensor 1 signal noise above limit. So both knock sensors are basically stating that they've gotten some loud knocking noise. And then what's the other one? So we've got naturally some position sensor for the Valvetronic, 2 codes for that, which those are common when the actuator fails. This one here, a Valvetronic output stage overload. That is one that I've not seen overly common. So there's a lot of concerning things here before attempting to sell something to the customer. Do we just take the approach of we've got a Valvetronic motor issue here and we just go about replacing it for them? Or are we going to do that, find out we've got a faulty DME driver caused by the Valvetronic motor failing? Or are we going to do a Valvetronic motor, a DME, then get it cranking running, only to find out we've got a rod knock or a bad engine? I don't know. There's a lot of questions to be answered that could be a lot of waste of money. Now, without throwing a major parts canning and just saying, let's do an engine, I'm trying to break down and decipher what's really going on with this whole mystery. First thing that I did was to pull the oil filter. Basically, check the oil condition and see if there's any bearing material in the filter element, which it is an aftermarket filter, but in the element I don't happen to see any bearing material, neither in the oil that's in the filter housing. So that's kind of a good sign. It's telling us possibly that none of our bearings are shot, but what I do want to do is crank the vehicle over. I'm gonna measure oil pressure here at this port. That's usually where the oil pressure sensor goes. On the newer versions, it's just capped off and there's a pressure sensor down low. So I've removed that cap screw. I'm going to put a transducer in this port, cover this back up, crank it over, measure my output voltages on the 3 legs for the 3-phase motor of the actuator to see if the DME is able to provide good voltage control on the 3 legs. So hopefully I'm trying to get an overall picture of the condition of what we're going to have going on to see if we've got oil pressure. We don't have bearing material. We'll check to see our output voltage from the DME, all while doing a relative compression also. Alright, we'll go ahead and crank it. Alright, I just saved that. I'm gonna restart it, but I maxed out my oil pressure reading. I had it just at 20 psi max. I didn't think it was going to get up that high or higher compared to other ones I've measured, so changing my scale, going to start that over. Alright guys, so here is the waveform that we just captured, and I'd like to go over some of the major points that the whole purpose of why we are capturing all the signals. So the one major one is going to be down here in green. We want to see if we can build oil pressure. We don't want to first and foremost do any type of work if we know that we do not have oil pressure being built up, because it would mean the oil pump chain would have come apart and possibly given us some those oil pressure codes. Obviously, we at crank up, we shoot straight up, drop off a little, but then maintain as we crank, and we are at 23.5 psi during cranking. So that's the first one to check off as far as having something in question. We don't have to worry about no oil pressure. Next, let's do a basic just relative compression. We'll use ignition in our starter, current draw, and we'll look at this. So it's a little bit odd, but we are getting 4 cylinder humps and an ignition strike. So one in the red is our cylinder hump. So we've got 1, 2, 3, 4, and then blue is our ignition strike. Now I do want to kind of make you guys aware or familiar. For some reason, these N20s, BMWs, strike their ignition when cranking a little bit to the right from the peak point of compression. That's one thing that I've gotten to know on these, and it's a known good condition. So don't try to kind of look at it and say that the ignition is being delayed when it really isn't. Now it's a little odd. We've got 2 that seem a little bit higher than the other 2, but this vehicle's been cranked a million times with in the condition that it's in, so we could have some issues going on in the cylinders, wash down, and so on and so forth. But that's the relative compression portion, and then the other one, which is again very important, was for the Valvetronic portion of the DME. I've gotten to know on these, if Valvetronic actuator has ruined the DMEs, we will not get any voltage or full voltage out of the DME drivers for the 3-phase motor. And so I check voltage, not amperage, to see if we've got good full output voltage, and they are all the same and full. As an example, I've gotten them where the portion in the DME had been damaged and one of the legs would put out maybe 7 volts or just 5 volts, something that's odd and different from the other 2 legs. And that's one good way of determining if the DME is faulty or messed up. So seeing full voltage being put out on all 3 legs gives me the confidence that we don't have a damaged DME as far as Valvetronic actuation. So that, and there was that rattle that I was explaining on the Valvetronic, which is pretty common when the actuators fail. They'll try. The rattle is that the motor tries to move and it can't, and it's just stuck in the position and it rattles in place. So based off of this breakdown of waveform of all these measurements we're taking, The DME is good. Engine mechanical, as far as oil producing capabilities, it's there. We've got 4 humps. Our timing, our ignition strikes are there. So I think we are good to go and able to make a Valvetronic repair to get this motor in a electronically capable of cranking over and running and just idling, and see if that's all this needs. So based off of that, naturally, I went ahead, replaced the Valvetronic actuator motor, and what you are seeing here is me just basically clearing all the fault memory and then performing the resets, relearns, so on and so forth, all the standard procedures that I do and run through when replacing the actuator motor and getting it ready to crank over. Go ahead. Alright, so everything at this point is fine and dandy. The car starts, runs, and drives. It does have that extended crank, which was a little bit odd, and it kept doing it each time. I did notice the vehicle came in with low coolant, so I topped it off, and then I ran the water pump bleed procedure, and as you can see in the picture, a bunch of coolant came out on the floor. This vehicle, I guess prior to coming, had had some sort of a coolant leak, and it looks to be from the turbo coolant lines, which again I did not know because the vehicle came in not driving and was low on coolant, and I find out when I top it off. And then once it is topped off, and then the turbo lines replaced, the system is now sealed, and I could start run and drive. But I noticed that the coolant expansion tank was kind of bubbling and gurgling, and then it kept doing the extended crank. Okay, so here is the waveform for that cranking event, and blue channel is our starter current draw. So you can see we've got peak points, and one cylinder is continuously low. That's cylinder 1, 3, 4, 2. And then how do I know that? Red channel is our ignition sync. It's on cylinder 1. At that point we apply the firing order, and now those are top dead center for each cylinder, those peak points. Green channel is our pressure in the coolant system. As you can tell, this blue channel, when we first rose up, that's when our starter kicked out. We used up some amperage, and then that's when the pressure rose up. And on this one, actually, it stayed just pegged, maxed out the whole time during cranking. That means there is crazy high pressure in the coolant system. And if you look, we have a geyser. Well, we clearly have a blown head gasket, as you just saw. Now, I quickly just wanted to go over this waveform and explain a little bit about it. If you remember, this was the relative compression we saw in the first capture that I explained. And I'm pointing out the high cylinder hump, or the higher amperage cylinder that we saw there before, as I got marked with the arrows. Now, I've run into this one time before in another video, and the reason why one cylinder has more compression than the rest is because it has coolant inside the cylinder, and naturally liquids cannot be compressed and it creates more resistance, harder to turn over, and it raises the amperage. Okay, and so this capture, I just wanted to point out a couple things. This is the one from the video clip we saw when all the coolant was spraying everywhere. Green channel again shoots up, showing us high pressure in the coolant system. Blue trace is our relative compression, our starter current draw, and contrary to the one we took before the engine was running, we now have only one cylinder that is showing us to be low compared to the other three. Now this can be a little bit confusing, especially when we saw the capture where before we had one that was higher than the other. But I wanted to explain and show you why now it's looking this way and why we just saw the geyser exploding everywhere. And so what I think I'm going to use to try to help explain the whole difference between the two is our amperage levels. If you notice here on the crank no start situation, 3 of the cylinders were down at about 175 amps, and the one single cylinder with coolant in it was over at about 210. So there's a big difference, and we now know where the difference came from. It's from coolant in that cylinder. And so now if we take a look at this waveform, which can be confusing and maybe lead you down the wrong path because it looks like only one cylinder is down and low on compression, when in reality it's not. What's going on is if we use our amperage levels, which the low one is at 212 amps, and our 3 other high ones are over 230 amps. Now, this is after it's been running, idling, and just pumping coolant into the cylinders and also pressurizing the coolant system. But what we are seeing is an elevated level of amperage across all our cylinders during cranking, and that's from buildup of coolant into all cylinders, also along with pressurizing the coolant system, as you could see in the green channel, and naturally from when we relieve the pressure in the expansion tank. And also this will help explain that hard start, that extended crank, because not only do we have fuel being injected to help start the engine, it's mixed with coolant in all of the cylinders, and it's just hard to ignite the fuel mixture because we have coolant, and that's why we're having that symptom. And this is why we're seeing the way this capture looks like, is because all cylinders now are just compressing liquid, which raises the amperage, and this is where the difference comes in the waveforms. At this point, the customer has opted to go ahead and replace the head gasket. Alright, so we got the cylinder head removed, and this is the head gasket still on it. And you can see some burn marks there, and definitely there. And some coolant in cylinder 3. So here's the cylinder head. I've already cleaned off so I can take some measurements here on the surface. It did have burn marks here in the section between the chambers, but basically what I need to do before installing this one back on and have it be a waste of a job is to see how warped, if warped, most likely it is warped, just how warped this one is. And what I use is straight edge, and these 3 that I keep with the straight edge is usually the measurements that I use. So biggest one is 3/1000, check if it's warped that much, then 2 and 1.5. So I'm going straight for the 3/1000 first. So first measurement I want to check is down the middle where the looks like the warpness happened, and again it's 3,000. And it comes through there. As you can see. And back here. Middle. The front it starts to go. As you can see, definitely the middle, and the back is warped to that amount. Take a diagonal, comes through. The middles are usually always the most warped. Obviously comes through there, and then it's actually tight that way. Other way diagonal. So goes through easy and goes through. Lastly, this usually is not that bad, but looks like we got a little bit there even. That's pretty bad. If on the straight front to back on the edges, if it warps there, that's pretty bad. So we clearly have 3,000s worth of warpness that we've measured, and that's typically the largest amount that I'd like to see or have used or gotten away with in the past with other engines in these situations. On this one, I was a little bit just battling myself internally, trying to decide what to do, if I should put this back with the warpage that I measured. So what I ended up doing was getting on BMW service information and checking to see what spec they had. Theirs was in max allowable of 4,000 the long way and 2 side to side, we'll call it, across the head. And off camera, I apologize, I did use my 4,000s feeler gauge and it actually did not go through, and then the 2,000s across the way, both despite the fact that it was 3,000s warped basically the long way. It fell within the supposed allowable limit that BMW specifies and or lets you get away with. So despite the fact that I was kind of internally battering myself trying to figure out what to do, I decided to go ahead and kind of wing it, gamble, and put this one together with a new head gasket and timing components, so on and so forth. So here we are putting it all back together, some new timing components as I said, but as this vehicle has done, there are some more gifts that it has given me, all due to the overheating condition, some hoses, the radiator, also the intake breather pipe, so many gifts it's given me. All right, got it all put together, obviously. Off camera, I just did a crank no start for a while. I'd like to do that anytime I do timing work, cylinder head, even engine replacement. I like to just crank the engines over, have it build up some oil pressure, get it spinning while it's on, just set and base timing, just to make sure there's nothing odd, weird, or anything crazy. Now that I've got that over with, we're going to go ahead and do our first crank, start, run, idle. And last but not least, of course, this vehicle couldn't let me go with one more headache. This one was not really a gift from the vehicle, as opposed to more of a goof up from me. This was self-inflicted. I created this. Just basically didn't pay too much attention when connecting the DME back together, and I ended up bending one of the pins, which then just actually surprisingly let the vehicle start, run, and drive. But it was in a limp mode, kind of fail-safe. This is how I started it when you saw the smoke and everything, but it had multiple codes that definitely were not there before. And so just one more little issue to take care of when trying to finalize this whole repair. 2016 BMW 528. I wanted to bring you guys along to show you if you ever run into these trouble codes. They're not too common or don't often happen or come across here at the shop. The ones that I'm talking about is these with 5-volt sensor supply, with some other sensors, absolute pressure, the accelerated pedal, again with some related to short to earth or basically 5-volt, voltage too low, any of those weird 5-volt circuit sensors. You might want to, along with checking sensors, you might want to check the DME and look at what we have here. We've got a bent pin at one of the connectors. That's obviously not going to make any contact with the engine harness, and so in order to avoid chasing your tail, you might want to look at the connector first. Alright guys, so after all those headaches, all those some mishaps, just surprise after surprise, finally got it all put together. I drove it last night, got all the coolant, heat cycling, no more leaks, no more air pockets, no more gurgling in the expansion tank, none of the sort. Again, when I do major repairs, I like to drive it a decent amount of miles, and I did some last night and a little bit this morning. But let's get one last look at the start, and maybe I'll get to show you the mileage. Let's go ahead. So far I've got almost 60 miles on it. Let's listen to the crank up just to prove out obviously that we're not having an extended hard cranking start that we were because of the coolant in the chambers. So starts up right away, no more issues, obviously no overheating, no pressurizing of the coolant system. If I've driven it 60 miles already, pretty sure there's not going to be any more issues with the coolant system. So this one was definitely a crazy one, being how it came in, crank no start, and just everything that spiraled from there. But at this point we've brought it back to life, rectified the issues, should be able to go ahead and drive it normally. So hope you guys enjoyed this. This was definitely a roller coaster for me. That is all on this one, and hopefully you learned something. With that, I'll say goodbye, and again, thanks for watching.